We are back with the titration basics. What we are going to do is we're now going to take a look at what happens if one of the acids or bases is weak. So we're going to look at both situations. If I have a strong acid with a weak base, and then we'll look at if I have a strong base with a weak acid. So in this case, we are going to see that once neutralization happens, the pH doesn't stay 7 because you actually have hydrolysis. So what we're going to take a look at is how to handle that hydrolysis in order to figure out the pH. So like I said, because of hydrolysis, the pH at the endpoint does not stay 7. In this case, if we're using a strong acid and a weak base, hydrolysis is going to occur of the conjugate acid of that weak base. And you're going to see that the pH is going to wind up being lower than 7. So we've got to do two things to solve a problem involving a neutralization between a strong and a weak substance. So first we're going to solve the neutralization reaction. Then we're going to solve the hydrolysis reaction using an equilibrium constant for that weak material. So going back to the reaction that we did before, what's the pH at the equivalence point between a solution that is 0.125 molar HCl, but now instead of using sodium hydroxide, we're using ammonium hydroxide or ammonia. So you can think of it both of these ways. You're going to see that sometimes it's a little bit easier to picture it one way than the other, but numbers are all still the same. So first thing we have to do is the neutralization reaction. So here's what's going on. I'm taking HCl with ammonium hydroxide. If you think of it this way, it's easy to see what's going to happen. I'm going to get H and OH minus producing water, and then I'm going to get NH4 plus and Cl minus. That is a weak substance, so it's going to stay separated in ions. You're not going to have them come together. So you can write it this way, but think of it this way. So this is the conjugate acid of the weak base. This is the conjugate of the NH3, and that's what's going to undergo hydrolysis. So if we were to solve this titration equation, if all we were asked to do is figure out what volume of HCl we would need, you're going to see it's still 60 milliliters. So it hasn't changed from that first equation. Everything is going to still be required to neutralize the solution. So the volume of HCl isn't going to be any different. But it's just that once that neutralization happens, a secondary reaction takes place, and so the pH doesn't stay 7. So nothing different about the titration equation or the neutralization. It would still cost me 60 milliliters. But to get the pH, I have to consider hydrolysis. Okay, so the pH isn't going to be 7 because the conjugate acid of the weak base is going to react with water to produce H plus ions. So this is the hydrolysis reaction that's going to take place. The NH pluses, the NH4 pluses are going to react with water and produce some of that weak base back, because remember, with a weak substance, it doesn't completely ionize. So if I have all of these things, the kind of reverse reaction is going to take place. I'm going to get some NH3s. Actually, I'm going to get a lot of NH3s out of the mix because of the hydrolysis that takes place. Okay, so in order to figure out the pH, I've got to do three things. Determine the concentration of the NH plus at the endpoints. Then I'm going to solve the equilibrium expression for the H3O plus or H plus, whichever way you want to think of it, right? That's same thing as hydrogen ion, hydronium ion. And then I'm going to convert that concentration to a pH value. So going on to the next page, like I said, the first thing we're going to do is figure out what the new ammonium ion concentration is after the titration has taken place, because it's essentially a dilution problem. So we started out with 75 milliliters of the 0.1 molar NH4 plus, or NH3 technically. All of that, we're assuming all of it dissociates right away. But it was diluted to 135 milliliters because 60 milliliters of acid was used, right? We figured out 60 milliliters of acid was used. And we had that 75 milliliters of base. So 135 milliliters total. So the molarity of the ammonium at the end point is 0.0556 molar. So that's the first step. So that's our starting concentration for our hydrolysis reaction. So next thing I'm going to do is figure out what equilibrium constant I need to use. So the Kb of ammonia is 1.8 times 10 to the negative fifth. But I want the Ka of the conjugate acid. So remember that I can get Ka by dividing Kw by Kb. So Ka of the conjugate times Kb of the weak base is equal to the Kw. So I divide one by the other, 1 times 10 to the negative 14 by the Kb, and I get a Ka of 5.56 times 10 to the negative fifth. I know you're going to see a lot of 5.56s here. It just happens that the numbers that I picked all wind up giving us 5.56. So it's just a coincidence, I promise. So now I'm going to solve an ice chart, or a rice chart, right? The reaction, initial, change, equilibrium. So initially, I have a concentration of ammonium ion of 0.0556, nothing of the other two. I'm going to lose a certain amount of ammonium. I'm going to gain equal amounts of ammonium and hydrogen ion or hydronium ion. And so at equilibrium, these are the numbers I'm dealing with. So set up my equilibrium expression, plug in the numbers, and I get an H3 plus concentration of 5.56 times 10 to the negative sixth. Okay? So now that's my H plus concentration at the equivalence point. So I'm a little bit acidic. So even though I've neutralized everything, because of that backwards reaction, because of that hydrolysis, some H plus actually reforms in the solution. And so the pH, if I do the negative log, is going to be 5.25. So it's not super acidic, but there's enough there to make the pH not 7. So there's the idea. So once again, this is the reaction that initially takes place. This is the neutralization reaction. But once that's finished, hydrolysis happens. So I've got to figure out what's going to happen. How much of a reaction is this thing going to cause to create H plus ions in the solution? And I do that using an ice chart. And the Ka of the conjugate. So hopefully that makes sense. We're going to move on to now the opposite, titration between a weak acid and a strong base. So in this case, the opposite is going to happen. Because of hydrolysis of the conjugate base of the weak acid, the pH is actually going to be a little bit higher. So we're going to actually generate OH minus ions because of the hydrolysis of that conjugate base. So again, what you need to do is solve the neutralization reaction and then solve the hydrolysis reaction. So here's the situation I'm going with. So again, same values, same numbers as before. 0.125 molar HF, 75 milliliters of 75 milliliters of 0.1 molar sodium hydroxide. So now HF is our weak acid. Sodium hydroxide is our strong base. Neutralization reaction, HF plus sodium hydroxide gives me water and NaF. But remember, this is salt is very soluble, so technically I have these guys. F minus is my conjugate. Conjugate base of the weak acid. So I'm going to have hydrolysis take place. But once again, first I'm going to figure out how much HF it would take. So same calculation, same numbers and everything. I'm not using more than one H plus or OH minus in my acid or base. So I'm still going to use 60 milliliters of the acid. So now I know I have a total 75 plus 60. I'm back to 135 milliliters at the end. I'm going to need that. Okay, so hydrolysis of the F minus reacting with water is going to produce some of that weak acid, HF, which means there's going to be some OH minus floating around. So just the opposite of what we saw before. The F minus is going to pull the H plus off of water to make that weak acid, because not all HF dissociates in water, and I'm going to have some OH minuses floating around. So again, same set of calculations. Determine the F minus concentration, solve the equilibrium expression for OH minus, and then convert that to pH. So moving on to our last sheet. Once again, concentration of F minus is going to be obtained by doing a dilution calculation. So I had 60 mils of F minus at 0.125 molar, or not F minus, HF, but it's a 1-to-1 ratio, so the same thing, divided by 135 milliliters at the end. So my new concentration of F minus, the F minus concentration at the end point when neutralization reaction is done, is 0.0556. Now that is what's going into my rice chart. Okay, so the Ka in this case of HF is 6.7 times 10 to the negative fifth. Forgot to change that from the last slide. So Kb, the equilibrium constant for the F minus, is going to be 1 times 10 to the negative 14 divided by that, or 1.49 times 10 to the negative 11. So there's my Kb. Filling in my ice chart, just like I did before. The F minus reacts with water to produce HF and OH minus, so we get some OH minus left in the solution after all is said and done. How much actually forms? I'm going to solve my equilibrium expression. 1.49 times 10 to the negative 11, x squared, divided by 0.0556 times 10 to the negative x, gives me an OH minus concentration of 9.1 times 10 to the negative 7. So final step, figure out what the pH is. Well, the pOH is the negative log of that concentration. So the pOH is 6.04. pH is going to be 14 minus that, or 7.96. So again, it's slightly basic. So notice the difference between the two. Okay, so I did all the same solutions. So it's going to be similar above and below. Weak base is going to give me a slightly acidic solution. Weak acid is going to give me a slightly basic solution. So this hopefully makes sense. You've got some practice to do using just these kinds of calculations before we jump into doing titration curves. Please practice those worksheets so that you're practicing these calculations a little bit.